Here's our 2x2 table again. Make sure you understand what this represents. If you need a reminder, then go back to definitions and have a look. Okay, experiment 1. All measures of associations are currently at their null values. So risk difference is 0, risk ratio is 1, odds ratio is 1. See, because the risk is the same among the exposed as the unexposed, and so are the odds. Now we should set the number of cases among the exposed, that's x plus y plus here, to 60. Let's do that. The risk difference is now 3%. The risk ratio is 2. And the odds ratio is 2.06. The risk difference is 3% because the risk among the exposed is 6% and the risk among the unexposed is 3. So it's just the difference between those two. The risk ratio is 2 because you take this one divided by that one, and so you can see the risk is twice as big. And then the odds are almost a little bit more than twice as big among the exposed. So it's 2.06. These two are, the risk ratio and the odds ratio measure two completely different things really, but they are usually quite close to each other when the prevalence of disease is low. But you should be very careful in interpreting them as the same. So the odds ratio is not a risk ratio and the risk ratio is not an odds ratio. Okay, in experiment 2, we set the number of cases among the exposed to 600. Let's do that. And the number of cases among the unexposed to 300. Let's do that. The risk difference is now 30% because the risk among the exposed is 60% and the risk among the unexposed is 30%. This one minus that one gives us a risk difference of 30%. The risk ratio is still 2, okay? And the odds ratio is 3.5. So you see how the risk difference is telling you the difference between these two. The risk ratio is telling you the magnitude between these two, which stayed the same as the previous experiment. And now we can also see that the risk ratio and the odds ratio are quite different, okay? Because now the prevalence of disease is quite high. What happens if we set this to 900 and this to 450? Now the odds ratio is 11, okay? The risk ratio is still 2. And the risk difference is 45%. So the risk ratio in this case is the same in all our experiments, but the real true risk difference underlying that risk ratio is very, very different, right? We go from 3% risk difference to 30% risk difference to now 45% risk difference, but the risk ratio is telling you the same thing. The odds ratio is changing wildly. Maybe that can be interpreted as a good thing. It's really showing that these different risks are different. But then again, the odds ratio is quite difficult to interpret. Have a play around with this to make sure that you understand it.